We're recording, so that's recording. Okay. So, at this point, the note is now going to be called, oops. This note is now going to be called, and I'm just looking at the corner, ray diagrams. So we're going to do something called ray diagrams for plane mirrors. All right? So what we've been using up to this point are plane mirrors. And when we say plane, we don't mean boring. Oh, these are boring mirrors. What do I mean by plane? Yep, they're flat, like a plane. All right? So they're plane mirrors, so they're flat. What do ray diagrams do? Ray diagrams allow us to find images. So they allow us to find images. So what I'm going to do is I'm going to draw some diagrams. Here I've got a mirror. And I'm going to imagine that I've got an object out in front of that mirror. In this case, you can see I've put a paper clip out in front of the mirror. Can you see it there? Yeah. And you can see there's an image of the paper clip in that particular mirror. We want to use rays and the law of reflection to find this. So here's how we're going to draw this up. Again, I'm going to use my protractor and I'm going to draw a mirror, and this time the mirror is going to be up and down, as if we're looking into the mirror. And I'm going to put the back of the mirror on the back side here, just like we've been doing all the way along. And in order to find an image, I must start with an object. So I'm going to draw an arrow. And I'm going to draw that arrow on a little bit of an angle like this. An arrow right there. And that arrow is going to be my object. I'm actually going to label it with an O to represent the fact that it's my object. And now I'm going to try to find its image in the mirror. Okay? Now, there's a technique that we use whenever we want to find an optical thing, like an image or a shadow, and we've already talked about it. I don't know if you remember. How many rays did I need in order to locate the shadow when we were drawing our shadows? We needed 2. And that's true for locating images. I need to locate 2 rays. And the reason we need 2 has everything to do with our brains. Our brains are very powerful things. Our brains have the ability, along with our eyes, to locate where rays come from. So when rays strike something, they spread out and they enter our eyes. And then our eyes are very good at working backwards to locate where the rays came from. And that's how we locate an object. So if I have a ruler here and I've got the ruler out front and the light is hitting the edge of the ruler and is spreading out, those rays enter my eyes, and 2 rays are enough for my brain to locate where that ruler is. So we need 2 rays to locate the image. Yep?
So it's like if someone, I'm sitting like this, and then say Nolan shines like a mirror in my eye, and
yep.
I just turn and immediately know where it is
because your brain is able to work its way backwards and locate where those rays come from. Whether the rays come from a real thing like a pencil, right? So the rays separate from the pencil. My brain is able to work its way back, so I'm able to touch the tip of the pencil because my brain's able to do that. Whether it comes from a real pencil or whether it comes from an image of a pencil. So if I'm looking at the pencil in the mirror, there's got to be rays coming from that mirror that make me think that there's a pencil in the mirror. Now, I just said that our brains were really smart because we're able to work our way back. But our brains are actually easily tricked. My brain cannot distinguish the difference between a real pencil and a virtual pencil that's in the mirror. The only way that my brain can tell the difference is if I try to go out and reach it, I either get the pencil or I bump into the mirror, right? But my brain can't tell the difference. And that's why a mirror works the way it does. When the rays bounce off, my brain thinks they came from in behind the mirror. And that's what we want to find. Yep?
But how come I can tell that there's no pencil? 'Cause you know-
Sorry, what's that?
How come I know that there's no pencil in the mirror?
The reason you know that there's no pencil in the mirror is probably because you can see the edges of the mirror and that you've had experience with mirrors and you know the way a mirror looks if it sits in front of you. But if I took the entire back wall of the classroom and I swapped it out for a mirror, all right, and I had the front wall look like the back wall, then you would be completely tricked into thinking that that back wall was a real thing. Don't do that. I don't have time to play games, but they're good questions. So you could be tricked to think that it was a mirror. You've all experienced this. If you've walked through the mall and you're walking along, you know how they got lots of mirrors at the mall?
Yeah.
I don't know if you've ever noticed where sometimes you might go, hey, look at, there's my buddy over there. Oh no, wait a minute. Oh, he's over there. Oh, I saw him in the mirror and I thought it was him, but my buddy's now actually over here. You know, if you might have actually made a move towards the mirror. Hey, oh, no, that's a mirror. I'm embarrassed. I hope nobody saw me. And that's because we can be tricked by mirrors. The fact that we can see the edges is what gets us here. Okay, so we can actually use this little mirror to kind of help us solve the problem. Take a look here. If I bring a mirror actually up to this, then I'm going to open that up a little bit. You can see that's where the image is. We want to find that using rays. All right, so I need a protractor. Here's how we're doing this. Everybody kind of catch up. I'm going to take a ray, and I'm going to take a ray off of the top of this arrow, and I'm going to bounce it right there off of that mirror.
I see.
Now, where's that ray going to go?
Doesn't matter what angle.
No, it doesn't matter. Just put it up. Where's that ray going to go?
Through and down.
It's not going to go through. It can't go through the mirror.
It's gonna reflect.
It's going to reflect, and it's going to head up in that direction. We now need our protractor in order to find that. So we're going to do just like we did. We're going to mark a normal. So we're going to mark a normal. I'm going to do the normal a little differently this time. Notice I put the 90 on the mirror, and there's the normal right there. And look at, I can actually measure my ray straight from this. My ray's right there, 10, 20, 30, 40. So if I draw my normal, I can actually put in here 40 degrees. Now I can flip my mirror around. Eric, are you drawing this? You need to swing your legs around and you need to draw all of this. I can swing my mirror around, put it on 0, and I can measure out to 40, and unfortunately mine's going to hit way up here. And then I'm going to draw that ray that heads out like that. All right? Now, if my eye was up here, and I'm not going to, you don't have to draw this, but let's say I had an eye right there. See my eye? It's a nice looking eye. See that? That ray is going to enter my eye, and my brain is going to think that that ray came from somewhere. Where does my brain think this ray came from? Yep. It probably can't even see the mirror, so I don't necessarily know that it came from the point on the mirror. It actually thinks it came from behind the mirror. Okay? So what we do is, we take this ray, I'm going to put my protractor back on it, and we extend in behind with some dashed lines. Okay? There's one ray. My brain cannot locate the tip of the arrow with just one ray. I need a second ray. So I'm going to do the same thing with a second ray. But you might think, oh man, I got to measure a bunch of angles. There was a really convenient ray that we found yesterday that's easy to measure because it comes back on itself. What was the angle of that ray that came back on itself? Ready? 0. If I take the protractor and I put it right on 90 on the mirror, and I bring that straight edge up just to the tip of the arrow, right here, see how I've got the straight edge on the tip of the arrow? That ray is now at 0 degrees on the normal. A ray that hits it, where's it gonna go?
Back at it.
Right back. And if it's gonna come right back, my brain is gonna think that it came from behind. It goes in, it comes out. Now, let's analyze this. This ray right here is spreading out. This ray right here, the one that's coming back out, is spreading out. What does my brain do when I see those spreading out rays? My brain thinks that they come from there, that point behind the mirror. That's where the tip of my arrow is. And that is the image. All right?
This is crazy.
Now, I need to find the bottom of the arrow so I can complete the overall image of the arrow. I'm going to show you a shortcut. Now, on the assignment that I'm going to give you later on, I'm going to let you do one part, the top of the arrow, with angles, and the second part, the bottom of the arrow, with the shortcut. Don't use the shortcut for everything, shortcut people. I'm not picking on anyone in particular, I'm just saying. How far away do you think, if we were to describe the location of an image in a mirror, how far into the mirror is the pencil? Yep.
Closer, isn't it?
Is it closer? What do you think? How far into the mirror is the pencil? What's that? It's actually the same distance behind the mirror as the pencil is in front. It's actually the same distance. If we had a curved mirror, that's going to change things. So let's test that. Let's take our ruler, and I'm going to measure from my arrow to the mirror. Now for me, that measurement is 2 centimeters. Do the same with yours. From the object to the mirror, I have 2 centimeters.
I think 1.4.
1.4? Awesome. Nothing wrong with it.
Yeah, 1.1.
Awesome. Write down whatever you've measured. Now let's measure how far the image is in behind. And look I did a nice job because mine is 2 centimeters. Now, if your angles weren't perfectly on up here at the top, if you measured incorrectly, yours might not be the same distance.
Yeah, I got it.
If you're close, that's great. If you did it, nice job. If you didn't, don't sweat about it. Because if you make a little mistake on the angle, it doesn't work. But I'm not concerned about that. So let's use that shortcut. Let's measure from the bottom of the arrow to the mirror. All right? And I'm actually going to draw a line there. And mine is 1.4 centimeters. And I'm now going to then put 1.4 centimeters on the back side. 1.4 centimeters. I'm going to draw the line on there. 1.4 centimeters. 1.4 centimeters. And now I have the location of the bottom of the arrow, which means now I can connect the top and the bottom of the arrow. And I've created my image. I'm able to find where the image is located compared to the object. And if I bring the real mirror into there, hopefully you can see there, we've got that there. If I bring this up, let's see if we can get into the right spot here. I bring that thing up there. Whoa, fun. You can see there, it doesn't matter whether I've got an actual mirror image or my picture. That's a little off, but it's not so bad, okay? Now, what we want to do at this point is write down something called image characteristics. Image characteristics. I should have put a capital C on that. Image characteristics. There are 4 ways in which we can compare an image to its object. So image characteristics compare images to their original objects. Original objects. Okay? And we use an acronym to help us memorize this. The acronym is SALT. Right? So the letter S stands for size. How is the size of the image compared to the object? How is the size of the image compared to the object? Well, for a plane mirror, what is it? Actually, SALT, and I'll put here, I want to put off to the side. For a plane mirror. All right. For a plane mirror, 2 R's in there. If I go up here, how's the size of the image compared to the object? How would you describe it? Same. It's the same size. Same. What are other options could it be? Smaller or larger? Larger, smaller, or the same? In this case, it's the same. All right. A. A stands for attitude, and I spelt it wrong. Attitude. Attitude. Actually, I'm going to put over here off to the side. I'm going to put off to the side. This is for a plane mirror. I'm going to put off to the side here. So for size, it could be larger, smaller, or the same. All right? Attitude. Attitude. Attitude isn't whether it looks happy or sad, right? Because it's got like a bad attitude. It has nothing to do with that. 2 options for attitude. It's either upright, all right, or upside down. We say inverted. Actually, years ago, we used to say instead of upright, the term we would use is erect. Yeah, we'd say an erect image. You may giggle if you'd like, because stating erect image is something you can giggle at. But you guys are very mature. You're not giggling at erect image. Excellent.
They use that, whatever it's called, in building to, like, we have to erect our building or something.
Yes, that's right. Yep. So you can use erect if you'd like, if it makes you giggle. All right. So what is the attitude of our image compared to the object? Is it upright or is it inverted?
Upright.
It's upright or erect. Sorry, I can't help it. I'm just a juvenile at heart. So it's upright. L, location. Location is a tricky one. Location. For location, you've got to compare it to the optical device. Compare the image location to the optical device. Compare to optical device. In this case, the optical device is the mirror. So where is the image compared to the object compared to the mirror? How far is the image, and where is it, compared to the mirror, compared to the object? Where is that image?
2 centimeters.
I don't want numbers. I want in general.
The same.
Close. To the right.
We don't want to the right, because what if I did this?
Symmetrical?
Symmetrical, somebody described it. It's the same distance behind the mirror. All right? It's the same distance behind the mirror. Same distance behind mirror. All right, and the last one, type. The type of image it is. And type can be 2 things. It can be real Or it could be virtual, which is right, fake, but virtual. Virtual. Like virtual reality, not real, right? Real images, by the way, can be projected. All right? Real images can be projected. Right now, my projector is creating a real image of this particular piece of paper on that screen. But I can't take a mirror and simply project a pencil onto a screen. It doesn't work that way. All right? This image of the pencil is virtual. Another thing about virtual images is you have to look into the mirror to see it. So in order for me to see the pencil, I have to actually look into the mirror to see it. So virtual images, you've got to look into the mirror to see it. Yep.
What if you have that thing in front of a mirror and you have another mirror like facing that mirror? And
Yep.
you look into the second mirror?
Yep.
Would that still be virtual?
Yes, because you'd have to look into the second mirror to see that. Yep, the multiple mirror situation. We might look at that in a moment. So what type is this for a plane mirror? What is it? What type is it for a plane mirror?
Say real.
What do you think?
Virtual.
I got to look into the
Yeah.
mirror. It's virtual.
Wow.
Virtual. So, for a plane mirror, when we do a ray diagram to locate its particular image, we find that it's the same size, it's upright, the distance of the image is the same distance behind the mirror, and it is virtual. Okay, so at this point, what I'm going to do now is I'm going to talk about a few little things to finish the class, and then I've got a little worksheet to give you, and we'll go from there. So I'm going to switch this over to here, okay, and I'm going to shut this off.